Good afternoon. Today is lecture number 9, and this is the second lecture on Newton method for optimization. And we will start with another alternative view as a method for solving of nonlinear equations or system of nonlinear equations, which probably you are familiar with this idea of Newton method from analysis. So suppose we like to find the minimum of f of x when x is n-dimensional vector. So if we know that a minimum exists, we can instead try to solve for optimality condition. So what is the optimality condition? Gradient f of x, which we denote usually as g of x, is equal to 0. G is a vector, so each of its components should be 0. It means that we are trying to solve system of nonlinear equations, because in general G is a nonlinear function. So let's write this. We have to solve a system of n nonlinear equations. G I of x is 0, I 1 to n. Okay. How can we do this? Let's think in this way. Suppose we stay at some point xk, and instead of looking on nonlinear equation, we will expand linearly our gradient, so we will build the linear approximation of the gradient, and analytically we can solve linear system of equations, and this will be iteration of our method, and we will repeat till the method will converge. So if we are staying in some point g of xk and giving some increment, moving a bit on step d, this is approximately g of xk plus Hessian at xk multiplied by d. So it's one can think of so g is my first derivative. So what is differential? What is increment of first derivative? It's the second derivative multiplied by increment of x. Or if I can remind you other relation which we already learned, the differential of g is h multiplied by dx. Actually, those two expressions are closely related, because you can think of differential of g related to g of xk plus d minus g of xk. So it's exactly what we have. Okay. So we have this expression for gradient, linear expansion, and as I told, an idea is to equalize this to 0. We say that we want that linear expansion would be 0, and what this will give us. So H is the matrix. So we have an equation H d is equal minus G, and then we get D is equal minus H inverse xk multiplied by G xk, which is exactly a Newton step we already learned in optimization context. So how, we can give a graphical illustration for this. For example, we have G, one-dimensional example, of course. G of x is some nonlinear function, and suppose we are staying at the point xk, and we build a linear expansion. We build a line that touch our graph at the point xk, and then we are looking for intersection of this line with 0, and this will be our new point xk plus 1, and then we build another linear approximation. I will put arrows showing how, in which segments we move. So this will be xk plus 2, and so on. And we have a rather fast convergent algorithm. Okay. Now let's move back to the optimization context of Newton method. So, as we're told, here is our direction. We can call it dk, and then we will do line search, one-dimensional optimization in this direction. And what we would like, the dk would be direction of descent. It means that directional derivative in the direction dk should be negative. So I can write f tag d at the point xk is equal to gk transpose dk. I remind our notation that gk is g of xk, gradient of the point k. So let us substitute So, and actually it's more. Okay. So, and I substitute dk here. So I get minus gk transpose h inverse hk inverse gk. And this should be less than 0. So minus some expression is less than 0. It can be always satisfied. So without minus, this product should be larger than 0 for all non-zero gradients. And actually it is satisfied if matrix H is positive definite. You can write this formally. This condition. So it's for gk non-zero, of course. This is satisfied if matrix H positive definite. I remind it's the same like to say for symmetric matrix all eigenvalues should be positive. But if our function is non-convex and we are staying really in the point when Hessian may have some negative eigenvalues, the simple idea is to check it somehow, and if it's so, to modify Hessian by adding a diagonal, say constant diagonal or some other positive diagonal. So if not, if it's if H not positive definite, then add positive diagonal. One can call it delta k, such that h k plus delta k is greater than epsilon I. What does it mean when I write such kind of expression? It means, actually, one can easily show, it means that eigenvalues of this matrix all should be larger than epsilon. Or I can say that this matrix minus epsilon by identity matrix should still be positive definite. Try to show it yourself that this is equivalent. So it means that h k plus delta k minus epsilon I greater than 0, and it's the same like to say lambda I hk greater than epsilon for I from 1 n. And after this modification, one can use so-called modified Newton method, and we will compute modified Newton direction just using this new matrix instead of Hessian. Is H k plus delta k inverse multiplied by gk. Okay. And this is a modified direction of modified Newton method. Okay. Now, Newton system is using Hessian matrix, which is O positive definite, or we may modify it. So the natural question is, what are good methods of linear algebra to solve symmetric positive definite systems? I mean, a system of linear equations where matrix A is symmetric and positive definite. And the convenient way of this is using so-called Cholesky factorization. It means that one can represent a symmetric matrix A as a product L transpose, where L is a lower triangular matrix. I mean, it has non-zero entries on diagonal and below diagonal, and what is above diagonal of this matrix is 0. And we will not explain the technique of this factorization, and it can be found in many books, including the book of Nocedal and Wright. I just want to mention that it takes about n cube operations. N cube divided by 6 operations to do such factorization, and numerically it's a very good and robust procedure. To get some feeling of this number, let's think about how much would take just to multiply 2 square matrices. It's for every element of product we need vector by vector n operations, so altogether it's n cube operations. So to find those factors, which is a major effort, as we will see right now, for solving system of equation, is about 6 times less than just to multiply 2 matrices. Okay. Meantime, let's think about some simple case. Say if we will have some system of equation, some auxiliary system, which we will need right now. Ly is equal to, for example, to B. How to solve this system? Let's write how the system will look. is like L11, B1. It's only one element in the first row, and all others is 0. Is equal, sorry, Y1. Y1 is equal to B1. And the second row will give us L21, Y1 plus L22, Y2 is equal to B2. We can continue. Let's say about 3 by 3 system. L31 Y1 plus L32 Y2 plus L33 Y3 is equal to B3. And it's easy to see how we will solve this system. First we can express Y1 in the first equation. It's just B1 divided by L11, and then substitute it to the second equation, and then we will be able to find Y2, and so on. So it's altogether it's of order n square operations. To solve it, and the procedure is called forward substitution, by forward substitution. So you see the procedure is cheap relatively to factorization, which is n-cube operations. Okay, so we had the original system of linear equations, and we factorized matrix A. So this is our new system. How solve it efficiently if we know that a system with single matrix L or L transpose can be solved fast? So it's very easy. We denote this product as Y. So we first solve a system L Y is equal B. And then we solve by forward substitution. And then when we found Y, to find X, so we denote Y as L transpose X. So we need to solve L transpose X is equal to Y. So this will be upper triangular matrix, L transpose. So then the last equation will have a single element, and we will substitute from last to the first, sequentially moving up the matrix, and this is called back substitution. Back substitution. Okay. So, and this is of order of n square operations. Okay. The only remark to say that even if matrix A is not positive definite, there is a modification of Cholesky decomposition which will automatically find also update, diagonal update of the matrix A, which will force it to be positive definite. So we don't need to think separately about finding this diagonal matrix. So the title is Modified Cholesky Decomposition. Decomposition or factorization is the same. So it's a procedure which does the following. It finds the matrix L such that L transpose is equal to A in our case, A plus delta, where delta is a diagonal matrix. So you see, you have here L transpose, a product of some matrix by its transpose. It's a common fact of linear algebra, and it's very easily to prove that any such product is at least positive semi-definite. It cannot have negative eigenvalues. So we found such delta that A plus delta is positive semi-definite or positive definite, and it's also we found factors of it. So let's write it down formally, that delta is built automatically in the process of factorization. And there exists a procedure function in MATLAB which does this work, and the link to this function can be found on our course website, and Dori will give it to you. And also from my website, I think you can find the link to this function. Okay, now we will turn to a special case of Newton method for solving so-called least squares problems, which is a special kind of optimization problem, and we can take an advantage of specific of this problem. So let's consider a vector function g from Rn to Rm. And what do you want to do? We want to solve an equation g of x. I will write approximately 0 because it may be that exists exact equality of 0 cannot be provided by any x. So we are looking for such x that the components of vector g are as close to 0 as possible. For example, in the sense sum of squares of the component. And in this way, we will solve a problem, find minimum of f of x, minimum over x in Rn, which is, for convenience we will write half, second norm g of x squared, was the same as half sum of gi of x squared, I from 1 to n. So we put some penalty on non-zero of gi. In our case, this is a square penalty. We can write it in a general way. For example, this is gi, and this is my penalty function phi. So now I have chosen quadratic parabola, 1/2 ga squared. But also other function may be used. For example, non-differentiable absolute value of ga, or many other functions. We now concentrate on smooth functions, but not only on quadratic one. So we will like to write it in general. F of x is just a some function phi of gi x, I from 1 m. And this generic expression, we will try to analyze it to write it gradient or Hessian. And the expression we will get, they are useful not only for these square problems, but also in more general cases. And we will move to constraint optimization, consider penalty function methods. Okay, now our goal is to write gradient and Hessian of phi. Okay, here is our function. I will not write derivation of the gradient and Hessian, just write the final expressions, and I suggest you at home to derive it. Not very large challenge, but it's very useful work. So try to do it. So this is a formula for gradient. Sum, I just will write sum over I, phi prime of gi of x multiplied by gradient of gi of x. And the Hessian will have two terms. So the first one, sum over I a second derivative of phi of gi of x. I will skip some time argument x to make my notation more short, but you understand from the context what does it mean what I'm writing. Gradient of gi at the point x, gradient of gi transpose. So what is written in this term? So this is a column multiplied by row. So this is a matrix. Such matrices are called rank 1 matrix. It has only one non-zero eigenvalue, and eigenvector corresponds to this gradient of gi. And the second term will be phi prime of gi multiplied by Hessian of gi of x. Okay, and of course the sum is over both terms. This is an important formula, and it will come, as I told, again and again in our course. Can I write this in the matrix form? Let's try to do it. Let's denote a generalized gradient of g, where g is not scalar but a vector. It's a matrix with columns gradient of every component of g. It's a matrix the following one: gradient of g1, gradient of g2, gradient of gn. And let's also say that when we are taking a function phi prime of some vector g, we mean coordinate-wise function. It's a vector which each component is like phi prime of g1, phi prime of gm. And also we will need a diagonal matrix which we will call capital phi double prime, diagonal matrix of second derivatives. So it will be phi double prime of g1, phi double prime of g2, and so on, phi double prime of gm on diagonal, and all other entries are zeros. Okay. And then we can write a compact expression for gradient. I have not too much room left on the blackboard. Try me to put it here. So the gradient in this case x will be gradient of g. this is a matrix, like we told, multiplied by phi prime of G. Let's see. It's really so. So if I have a matrix with columns and multiply by some vector, it's the same like take the first component of this vector multiplied by first column of matrix plus second component of the vector multiplied by second column, and so on. So it will be phi prime of G1 nabla G1, phi prime of G plus phi prime of G2 nabla G2. So we are consistent with this formula. Okay, and the expression for Hessian will be nabla squared f of x. So the first term will be gradient g of x phi double prime of g. I will skip x sometimes to shorten a bit formula. Gradient transpose g of x, and plus the second term. Meantime, I will just leave it as it was. It will be sum over I phi prime of gi Hessian of gi x. One can try to manage also the second term in matrix form, but it's now sum of matrices, so one needs to manipulate with three-dimensional objects like tensors. I will try to avoid it. Okay, and as I already told once, I suggest you to check this formula at home, to feel free with this matrix vector manipulations. And now let's come back to the least squares case. So as we told, our penalty for non-zero, this is function of one argument, which we'll write like t. So phi of t will be 1/2 of t squared. And of course, we will need phi prime and phi double prime, first and second derivative. So phi prime of t is equal to t, and phi double prime of t is equal to 1. So the matrix phi double prime is diagonal matrix. Second derivative is just identity matrix. Okay. So what we will have if we substitute g as an argument of t, and this is of course a vector function, we will immediately get gradient of f of x is equal gradient g of x multiplied by vector. This is a matrix multiplied by vector g of x. And the Hessian will be the Hessian. I should just write here identity matrix as I told. So it's gradient of g from x gradient transpose g x plus so phi prime will be just gi itself. Phi prime of t is t as sum over I g I of x multiplied by Hessian gi of x. Okay. Rather compact expression. What is the idea of Gauss-Newton method? Let's write our new title. Let's think what will happen with Hessian when we come close to solution, and if we are lucky and in solution vector gi really becomes small. I mean components gi become close to 0, and you see that the second term becomes small. Therefore, the dominating part of the Hessian will be given by the first term. And this is the central point of Gauss-Newton method. So the Hessian is equal approximately gradient of g x gradient transpose of g. And we just will denote this as a matrix H of x. So in our case, H will be not actual Hessian, but it's some kind of approximation. By the way, here we have a product of some matrix by transpose. So as we already told, this product should be at least positive semi-definite, or if this matrix is of full rank, for example, it's a wide matrix, and the rank is as number of rows, it will be even positive definite. Okay. So, and what is Gauss-Newton? It just write Newton method using this as a Hessian, and this, of course, is expression of gradient. So we can write that x k plus 1 is equal xk minus inverse of Hessian, alpha k is step size, and then H inverse of xk when H is this matrix, and then we should multiply by gradient, and this is the expression, gradient G xk multiplied by G of xk. Okay. And if H is singular, if some eigenvalues are zero, if, as we have told, they cannot be negative, but they can be zero, then as usually we use some diagonal addition, which may be obtained even by Cholesky decomposition. So if H of xk is singular, use H of xk plus some delta k, where delta k is a non-negative diagonal matrix inverse, instead of H of xk inverse. And as I told, it may be obtained, say, by modified Cholesky algorithm. Another version is to use just to add the diagonal just identity matrix multiplied by some small constant epsilon. Alternatively, use HK, use H of xk plus epsilon ki inverse, and this kind of modification has its own name, Levenberg Marquardt. And those approaches, Gauss-Newton and Levenberg Marquardt, are really efficient and very popular, and you will find them, for example, in MATLAB toolboxes. And with this, we finish our second lecture of Newton method. Thank you.